And until now, like we're pretty used to finding area under a curve, and we know that that's an integral, okay? Until now, we basically had, a curve, and then we wanted to find area. Basically, it was one curve. We wanted to find area, and when we use the term under the curve, we meant, the region between the x-axis and the curve, right? So that could look, like it could be above or below or whatever. Okay, fine. But what if you have more than one curve? Okay, so suppose f and g are continuous functions. It's all about being continuous. And suppose f of x is greater than g of x, right? Which means physically, if f of x is greater than g of x, like physically it sits above vertically g of x, okay? Throughout a and b, then what is the area between the two curves? Well, let's take a look. Okay, so suppose I have one curve like this. Okay, so suppose I have this is f of x. Okay, and now suppose also there is another curve, g of x. Okay, and do you see how f of x is bigger than g of x because it's physically higher than g of x, right? So now I want to find, going from here to here, from a to b, I want to find the area in between them, okay? So now, if I do integral f of x dx from a to b, what does that find me? That entire area, from the curve to the x-axis, all right? And if I do integral a to b g of x dx, what does that find? This area, right? But now, if I want to find this area in the middle, what would I do then? Subtract the two integrals, okay? So that's the idea behind this.
How would you do, like for this one, how would you do it if it's below the x-axis?
It all works out, okay? So then the area between the curves is this. The integral from a to b of f of x minus g of x. That's the same as a to b f of x dx minus a to b g of x dx. Remember how we learned if you have two separate integrals, you can combine the stuff in sine and so on and so forth, okay? All right, so what exactly is it that integral is doing though, okay? Remember, again, never forget what got you here. What got you here was finding area by first drawing rectangles. Do you remember that? So here, this is what we're going to do again. You have this region. You have an upper curve, y equals f of x, a lower curve, g of x. And you have to find the area of the region inside. So what we do is we divide this into an infinite number of rectangles. Okay? Now, if I take one representative rectangle here, okay, this one rectangle, LRAM, RRAM, it doesn't matter, that one rectangle, what is the width of this? It's the change in x, right? That's the base. What is the height of this though? The height is f of x minus g of x, right? So the integral, okay, is f of x minus g of x times delta x for every single rectangle. And then when I add them all up, again, it'll be f of x minus g of x times delta x, that's just dx, added up from a to b. So no matter how you look at it, it still comes out to that same integral. Okay? So again, the mechanism is it's dividing it into strips, and then each strip is f of x minus g of x. That's the height, and the base is delta x dx.
Why is the height f of x minus g of x?
Well, because this, right? So if you have, like here, if you have the height of this one right here at the very top, this one, right? How much is it to the very top of this? It's f of x. How much is it here? G of x. And then when you subtract, it's that balance. Okay? Okay. So, here we go. Our very first one. We want to find the area of the region between y equals negative x squared plus 6 and y equals x. So the parabola and the y equals x from negative 3 to 2. Okay? So you should know how these would look like and so on and so forth. You may or may not be given the graph. You should know how to reproduce it on your own. Okay, so the area that I'm looking for is this. And it basically is enclosed between this point and this point. Okay? Now, what you have to do first is you have to figure out the x values of the points of intersection between the two functions. If you're given the graph, then that's easy. It goes from negative 3 to 2. So the area is from negative 3 to 2, the upper function minus the lower function. The upper function is negative x squared plus 6 minus x dx. Okay? And so area, depending on whether or not you have your calculator available, you either do it by hand or plug it into the calculator. On the homework, I am totally fine for you to plug it into your calculator, okay? Because I want to focus on this and not the actual integral right now, okay? So the area will be 20.833, okay? All right. Super, super important to state this integral in like detail, in correct form, and then the answer. So normally, you know, if this was, let's say, on a free response question, this would be like part A of a question. You would probably be given 2 points for this, 1 for this, and 1 for this. On my tests or quizzes, again, same thing. This might be like 2 or 3 points, and this answer will be 1 or 2 points. So they have equal weight, pretty much. Okay, yeah. So the two functions, this is y equals negative x squared plus 6. This is y equals x. You subtract the two functions. So this is the blue function. This is the red function. Okay? All right, so let's do another one. Find the area between y equals secant squared and sine x. Okay. From 0 to pi over 4. So they tell you, you know, to go from 0 to pi over 4. So you don't need to find anything here. Now, okay, in this diagram, you're actually told which one the secant squared is and which one the sine is. Sometimes you'll just be given the graph without the functions being labeled. And it's up to you to know, oh, this is the sine and that's the cosine. This is the sine and that's the secant. Okay, so you don't necessarily have to draw it, but given the two, if you weren't given these,
but you knew those were the two graphs.
right?
Oh.
Yeah. So you would be given this. Well, also, so you'd be given the highlighted stuff and the graph, and you should know which one is which one, right? So you know that sine starts from 0 and goes up like this, right? And cosine starts from the maximum and goes down. And then secant, remember the graphs of secant? You remember how they used to look like this, right? So basically, you know for sure that this is how sine looks, right? And you can eliminate by, you know, process of elimination, all right? Okay, so here we go. So the integral here is going to be from 0 to pi over 4. What's the upper function? Right? Minus sine x dx. Okay, let's do this one by hand just because, all right? Because we need some practice with trig functions. So the integral here, so this is area. Area will be, what's the integral of secant squared? Tangent x, good. Plus cosine x from 0 to pi over 4. Okay, now let's plug in pi over 4. Tangent of pi over 4 is 1. Plus cosine of pi over 4, root 2 over 2. Minus tangent of 0 is 0. Plus cosine of 0 is 1. And conveniently, those 1's cancel, so it's just root 2 over 2. Okay, yeah. Okay, so here we go. Okay, so this one, you're not given the graph. It's up to us to do the graph. Find the area of a region enclosed by the parabola y equals 2 minus x squared and y equals negative x. Okay, 2 minus x squared, basically it's a parabola that has a vertex at y equals 2 and it goes down, right? Where does it hit the x-axis? 2 minus x squared equals 0, x squared equals 2, x is plus or minus root 2. And you don't have to be NASA precise here. Just know that it's between like negative 1 and negative 2, right? So here and here. Okay, that's good enough. Now I also have y equals negative x. That looks like this. Okay, just so we know how it looks, which one's above, which one's below. Okay, now we need to find points of intersection which are going to give us the limits of integration. Okay, so we're going to solve this equation. So where are the points of intersection? You take the two functions that you're given and you set them equal to each other and you solve for x. Cool? Okay, so 0 is equal to x squared minus x minus 2, x minus 2, x plus 1, so x is 2, x is minus 1, 2 and minus 1. Okay? Yeah.
So if you have the graph, then you could just look at the point of intersection. But if you didn't, then you would.
Correct. Then you have to find it yourself.
What was like the little major on the left there?
This one, I just wanted to know how, like when I drew the parabola, where it will cross the x-axis, so I could do like a proportionally, like, I could draw it to scale, more or less. Okay? So now, basically, so this is the region I'm integrating. So the rectangles are here, right? Each of the rectangles are these. Okay? My area then is the integral from negative 1 to 2. The upper function is 2 minus x squared minus negative x dx. Okay? And when you plug that into your calculator or you integrate by hand, you're going to get 9 over 2. How are we doing? So far, so good, yeah? Okay.
Is there a point in graphing it? If you...
Just to... No, not if it's on the... Well, the only thing is, so you know which one sits above and which one sits below, right? Because otherwise you would get the negative area. If you switch them, you would get negative area. Okay, so this is what I was talking about as well. Find the area of the region enclosed by the graphs y equals 2 cosine x and x squared minus 1. Okay, so suppose, you didn't have your calculator available and somehow like these points of intersection were given to you, right? Like in this problem, we have to find the points of intersection using the calculator. But would you be able to say which one of these graphs is the cosine and which one is the x squared minus 1, right? So which one is the cosine, the one above or the one below? Above. The one above, okay? So that's what I'm talking about. So this is what, this is y equals 2 cosine x, y equals x squared minus 1, right? It's not as scary as it seems, yeah? Okay, so let's figure out where those intersect. Okay, so we graphed both of them, and here are, here's the graph. you don't need to do much. You don't need to make it look exactly like the windows that you're given over there. But let's go ahead and find the points of intersection. So analyze graph, intersection. I'm going to find this one first. Okay. So that's the point of intersection, correct? Okay. What I like to do is I like to write down that that's the point of intersection. So what I'm going to do is I'm going to say this. We're going to pick a variable, A. Let A equal to 1.265. Okay? Then, what is the area integral going to be? Well, it's going to be the integral. Okay, and if you look at, you see how this is symmetric? I mean, it's a parabola, so you already know that the other one is going to be the negative of it. But if you don't believe yourself, you know, here we go. It's the negative of the A that you just got. So this integral here is going to be from negative A to A, 2 cosine x minus x squared minus 1 dx. Okay, and be very explicit. If there's parentheses involved, put parentheses or put the positive and negative signs equal to each other and so on and so forth. So now, here's what you're going to do. Go over to your point. Okay, hover over it and click on it. So it's highlighted like this. Okay? Now, do Control and this variable button, which is store. Okay? Type in A, enter, it bolds it for you. Yes? Now, that's stored in your calculator as A. Not truncated, not rounded, the whole darn bona fide number, Jonah. Right?
Wait, can you show that one?
It just gave me an error.
I'll do it again. Go on it. Go on it. You see where when you hover, it also says is linked to A. So go over it, hover on top of it, and click the center button, whatever this is called, right? That center button. Yep. Click on it so it's highlighted like that. Now do Control and variable on top of the 9. It's basically store, right? Like it says STO, which is store. So click on that. I didn't. Okay, so when you, all right, so Control, how come it's not working now? Right. A, enter. Now, if you want to be certain that it did what you wanted it to do, go to the home screen. Literally just type in A, enter, and it should give you that number. So now you know. Huh? There is a way, but you can, like, if you have to like overwrite it, then you can just.
You just say it. I tried to confirm it, but it didn't work.
Okay, so I'll take a look right now. But both on my assessments and on the AP test, that's how I want you to write it, negative A to A. Now go to the go to this menu, the toolbar, click your integral. Here you're going to go from negative A, tab A. You see how it's bold, right? Tab. Okay, now here's what we're going to do. Okay, don't start typing anything in. Yep. These are already stored in your graph. So do F1. Where is F? F1 of X minus F2 of X. Huh? Yep. And these are simple functions and it's faster. Like imagine if they're like complicated functions. Okay? Here we go. 4.995.
So when you store it, you're not only storing the A, you're storing the whole function.
No. It's just because it's in your graph. Okay? 4.1. No, there is no 1. 4.995.
Would it work if it wasn't symmetrical?
Yeah. No, if it wasn't symmetrical, then you could do A and B. Yeah. Now, when you do it this way, there could be a million of you solving the same problem and we would get a million identical answers, right? So there is no, oh, what if I was off by 1? What if I was off by 0.01? You're not gonna, because you graphed correctly, and everything right worked out well. So both on my test or on the AP test, there was like basically no leniency here, okay? You either get 4.994 or 4.995, and that's that, and that's that. Okay, whew, good calculator skills, okay. Right, and of course, we always have to throw a wrench in there. What if you have boundaries with changing functions, okay? So let's go back to some of the ones that we did. Let's take a look at this one. When you look at this region here, right, do you see how, when you look at this highlighted region here, do you see how from the very, very left of the region all the way to the very, very right of the region, no matter how many rectangles you draw, the upper boundary of the rectangle, the upper base is always the parabola and the lower base is always the y = x. Do you see that? Right? Whether it's over there or over here, it's all the same. And here it was the same. If I have a rectangle there, the upper one is always the cosine, the lower one is always x squared minus 1, no matter if I'm there or here or everywhere, right? Okay, take a look at this. Now I need to find the area of region R, that's this region here, in the first quadrant, bounded by y = √x, okay, and below by the x-axis and y = x minus 2. So now my region is this, okay? Now, is this the same as the ones before? If I take a rectangle here, the base above is √x. The base below is the x-axis. Do you see that? But if I take a rectangle here, the base above is √x, but the base below is x minus 2. So there are different regions here, right? And where does the crossover happen? At x = 2. So now what I need to do then, these are two completely different setups, two completely different rectangles. So I have region 1 and region 2. So my total area is going to be 1 integral in region 1. So going from 0 to 2.
Why'd you split it at 2?
Because that's where the boundary changes. Like that's where the bottom of the basis changes from this x-axis to that line. Yeah? So 1 goes from 0 to 2. Okay, what's the upper function? Y = √x. What's the lower function? Y = 0. So here I get √x minus 0 dx. Okay, obviously you don't have to put the 0. I'm putting it there right now to illustrate. Plus 2 to 4 √x minus x minus 2 dx. Okay? So that's with changing boundaries. So A is 3.333 here. Okay? All right. So you always have to see, do I have, the same boundary throughout or different boundaries throughout? Okay? It's like if you have a country, right, that's bordered between two countries on one side and then, bordered by other two different countries on the other side. Okay. And because that wasn't enough to, add variety, here's a little bit more variety. Integrating with respect to y. Okay, Sometimes it gets annoying to have to do this with two different regions and two different rectangles. Doesn't it make a beautiful diagram though? I mean, look at it. Like, look at how beautiful that is. Like, I could look at those all day. Like, okay, seriously, if I was walking down the street and saw that on a billboard, like, that's the city that I would live in forever, right? I mean, come on. Yeah? Okay. But when you're integrating over two different areas, it does become a little, like, tedious, right? What if there was another way? Who said the rectangles always had to be pointing like that? Why couldn't we have the rectangle on its side? Because then you would have, bases have the same, left and right? You can have the rectangles have the same bases throughout. Huh? Yeah. Because look at this one. Okay?
The other one is still with the boundary.
Oh, yes, but you could
always
always make y boundaries. Why just x?
Why just that?
Why just x? Aha, why not y?
Why is it always y? Like,
Why not y?
No, but actually, why not y?
Why not y? Exactly.
Everywhere, not just now. Like, why
Right,
everywhere?
because the functions are always given in terms of x.
Yeah, but why?
Right.
Because x is why?
Why? Okay. So, all right. So x. Okay. So look here. Look at this one. If I were to integrate over this region right here, when I'm over here, when I have a rectangle over here, right? The upper base is this function here. The lower base is this function here. When I'm over here, is the upper base and the lower base, are they the same as in the left rectangle? No. That would mean what I would have to do is I would have to split this up here, do one integral there, one integral there. That's a mess. But then, what if you take that rectangle and just flip it over? Make a horizontal rectangle, right? Now, look at this base and look at this base, right? Now let's do another rectangle. Okay, look at the base, look at the base. Are the bases to the left and right staying consistent throughout the region? They are, because whether you have the rectangle here, 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 the same base here and the same base here will be consistent. Okay, so that's a better region to integrate over. Now, before, when I had my points of intersection, right, I still have points of intersection, but before I went from x1 to x2, now I go y1 to y2. So I go from C to D. The only difference is now your functions have to be modified. You have to solve them for x. Okay, so it can't be y equals something. It has to be x equals something. So before, we were doing upper minus lower. Which one is the greater function here? The one to the right or the one to the left? Right. The one to the right. So you have to do right minus left. But now, it's all in terms of y. The variables inside are going to be y, 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 y. So this will be dy. And the boundaries are going to be y equals c, y equals d. Cool? Okay.
What does that mean?
Well, like y, because before it was like x equals a, x equals b. Basically, those are like y values now, not x values. So instead of a to b, we're going to c to d. Okay? So, for example, suppose one of the functions was y equals root x, and you want it to do it this way. First, you have to solve it for x. So you do y squared equals x, and then, you have x equals y squared now. So in here, it would be y squared dy. Do you see that? It'll all be in terms of y's. Okay, so let's do an example. In fact, Why don't we do the same example again? Right? I mean, we already put it on a billboard, so why not? Okay? Now, the region is going to be that same region here. It's just so satisfying to highlight that like that, okay? So now what we're going to do is we're going to create our rectangles this way. So if I have one rectangle there, the base to the right is that red line. To the left, it's the blue graph. If I do it here, same situation, okay? Right, red, left, blue. Okay. To do it in terms of y, I have the first function. Let me color code this. So that one was blue. Y equals root x. You solve it for x, and x is y squared. The other one, y is x minus 2. Solve it for x, it's y plus 2. Now, where are the boundaries, right? It goes from, the region stretches from y equals 0 to y equals 2. So, area is integral from 0 to 2, the rightmost function, y plus 2, minus y squared dy. Okay? Remember how we were saying, even from like the section 1, that this, and this are a unit? Do you remember that? Like there was a reason why I took so much time saying that over and over again, because we were going to section 2 today. And those two had to be a unit again. All right? So if you put this in your calculator, guess what you'll get?
3.333.
Yup.
How is one like more on the right?
Huh? So wherever you are, you know, the red function is always to the right, the blue is always to the left. Yeah? Okay, last one. Oh yeah, yours is two of the same color. But like the linear and the, yeah. Okay, now, so, such defeatists. Okay, so this one, find the area enclosed by the graphs y equals x cubed and x equals y squared minus 2. That's a sideways parabola. It's the inverse of y equals x squared minus 2. That's the inverse. Okay? Now, that's not a function. It's just a graph. I mean, it's just a relation. Okay, so most of the time, it's going to be up to you to decide which is best. Sometimes you're told to do it with respect to x or y. So what do you think? Which is best here? With respect to x or with respect to y?
Y.
Y, right? So remember, if it's y, if you're doing it with respect to y, the rectangles that you're drawing have to intersect the axis with you know what I mean? Like the axis with respect to which you're integrating. That's a mouthful, okay? So we're going to do it with respect to y. Okay, so here's what we're going to do. So this one, x equals cube root of y. And then here, x equals that. Okay, let me show you how to graph this. By the way, you can graph them as relations. Okay, so let's go here. Let's clear all this. Up, tab, up, clear. Okay, so look. Menu, graph entry edit. You can make these relations. So menu, number 3 is graph entry. You can make them relations. So now you can literally type in y equals, where's the equal sign? Here, x cubed. Right, you see it's that one. And then go tab, relation 2, you can type in x equals y squared minus 2. So you don't have to solve it for whatever it is that you're graphing. You see that? Tell me that's not like super cool.
It says I have,
Yeah, let's do it again.
it says I have a press to test graphing restriction.
Oh my gosh. That's like from 2019.
Really?
Yeah.
What am I supposed to do about that?
You come see me afterwards. I'll fix it for you. Okay. Menu. Window. Zoom. No, sorry. Graph entry edit. Number 2 is relation. Okay? Now, when you press tab or whatever, you'll get relations and you can type them in as they are.
Wait, click enter before you do tab.
Yeah.
So when you do enter,
Analyze
tab.
that.
To make relation
No.
to. Alright, what's relation to? X equals y.
Yeah.
2.
Okay, so now, menu. Analyze graph. Intersection. Wait, I pressed something else. Menu. Analyze graph. Intersection. Oh, what did I do here?
No, that's it. And then you hover, you have to click on the graph.
That's one of them.
It's weird.
Menu. 3.
What?
Relation.
Oh, I see. Okay. Here we go. Sorry.
How do you get to relationship?
Press tab. Menu, analyze graph, intersection. So here, you just, oh, shoot. Okay, here we go.
Here we go.
Okay, now here's what we're going to do. This time we're going from Y to Y, right?
I have a completely different answer for the same graph. Yeah. Mine is 1.214.
Oh, I changed it. Sorry. It got changed here. So what was this? Y squared minus 2? Because I dragged the screen and it changed it. Okay, here we go. Okay? Okay. So look, let me write down the integral and then I'll answer some questions. So look, we're going to go from Y to Y, right? So the integral is going to be from -1, that's the Y value there, to this Y value here. So you're going to relabel that. I'm going to click on it and I'm going to store it as C. Why C? Because I feel like C. Enter. Okay? 1.793. When you do that, you always had to put in here, let C equals 1.793. So here we go from -1 to C. Cube root of Y minus Y squared minus 2 dy. All right, you see that? Y. They're all in Y's.
Why don't you make the other one in relation to y? So y.
4.215 is the answer there. Okay, so now you can do the homework, by the way, for 8.2. And then next time we're going to review the homework, okay?
Wait,